Now let's look at an open system energy balance. So unlike the closed system, this open energy system balance, the actually two changes that I have here is, first, I've put a fluid inlet, so there could be mass that crosses the boundary, and a fluid outlet, which is mass that leaves the boundary. And there's something that I want you to note. Over here, this is an open system. I've assumed a fixed control volume. So right now you have a fixed boundary. As opposed to the closed system, in the closed system, I've assumed a fixed mass because there's no mass that leaves and no mass that's added to the system. And so I just want to make it a point for you to realize that even though I do have the dotted yellow line here, but the dotted yellow line doesn't move. It's fixed. So this is not a piston anymore. This is just a container that doesn't move. And this is just a fixed control volume. And the fluid that comes in and leaves interacts with the surface of this boundary. As opposed to in the closed system, we just looked at a fixed mass. Okay, so when it comes to open systems, obviously you can have fluid that enters the system through the surface, through the boundary, and then it leaves the surface of the boundary. And obviously still you could have heat exchange of the system with its surroundings and additional work from the shaft work that if you have a mixer, for instance, that is applied on the system fluid itself. Okay, so now let's look at what the energy balance looks like in terms of a time interval. So at a time interval, so let's say a finite time, let's say whether it's 1 hour, 2 hours, doesn't really matter. At the end, you want to look at the change in the total energy of the system. So again, the change in the total energy of the system over here will equal to the energy that is added into the system due to the fluid that enters the system, minus the energy that leaves with the system from the fluid that leaves the system, plus any heat exchange that is added to the system, plus any shaft work that is added to the system, plus any flow work that is added to the system, and I'll explain what that means in a second, plus energy generation. So that could be if you have a chemical reaction that's happening inside here, any electrical heat generation, any electrical energy generation, any electromagnetic or nuclear generation of energy, you'd account for that in this energy generation term. Now, flow work, you might be wondering, where did that come from? And you can't really see it over here. Well, flow work is usually associated with mass that enters the system and mass that leaves the system, because it's essentially the work that you need to push a fluid mass into the control volume against the pressure at the surface boundary. So let's say that you have air or liquid that you're trying to push in a pressurized tank. Then what you need is you need to have that liquid pressurized at least to the pressure of the tank in order for you to be able to push it inside the tank. And so that is the surface boundary work that you need to apply onto the fluid so that it could enter the tank. And you need to account for that somewhere, and that it's accounted for in the flow work. Also, as the liquid leaves the tank, the liquid will only leave the tank if it has enough energy to overcome the outside pressure. And in order for it to overcome the outside pressure, for it to be pushed outside of this control volume, then that means this control volume needs to apply a force, needs to perform work to essentially force the fluid outside against the outside pressure in order for the fluid to leave at the outlet. And so this needs to be accounted for, and we're going to do some simplifications so that you could actually see what it looks like when you expand these terms. Again, the energy of a system of a fluid contains internal energy, contains kinetic energy, and contains potential energy. This does not change. And let's look at the interpretation of all of these terms. So stored energy, which is the total energy change of a system, that's the change in the stored energy. This is the change in the stored energy inside the control volume. The flow in of mass into the system adds energy to the system due to advection, and that is represented by capital E in. And flow out of mass out of the system removes energy from the system through advection, and that is E capital E out. Heat flow into the system adds energy to the system, or if it removes energy from the system, let's say the system is hotter than the surrounding, then this Q here would be a negative number. Also, shaft work would add energy into the system. And flow work, as I said, that's the work needed to push a fluid mass into or out of the control volume against the pressure at the surface boundary. And energy generation over here can be a chemical reaction that generates energy into the system, or if you have any electrical energy generation, electromagnetic or nuclear energy generation, it would be captured over here by this energy generation term. Okay, so you might be wondering what is capital E in and what is capital E out? And that is a good question. So obviously the energy of the fluid entering the system contains its own internal energy, it contains its own kinetic energy, and it contains its own potential energy that you have to account for that is now being added to the system. Also, the energy that is leaving the control volume has its own internal energy and its own kinetic energy and its own potential energy that you need to account for or subtract from the system to make sure that you've considered all the energy that is leaving the system accurately. Okay, so let's now do some simplifications because it's important for you to understand the energy balance. So let's expand on the energy coming in and the energy leaving and flow work. So if we said, as we said, the energy coming in and the energy leaving can be expressed as the internal energy plus the kinetic energy plus the potential energy. And we said potential energy, the most relevant potential energy term for most heat transfer applications is the gravitational field, and that's why I have just the gravity potential energy over here reflected in the fluid's potential energy. And you multiply all of that with the mass coming in, and you subtract the energy leaving with the mass, which is also the internal energy of the fluid, plus the kinetic energy of the fluid, plus the potential energy of the fluid, multiplied by the mass of the fluid that's leaving the control volume. And then obviously you have the same term here, which is the heat that is being added or removed from the system plus the shaft work. Now, in terms of flow work is represented as the pressure at the boundary for which the mass flow is trying to enter, multiplied by the volumetric density of the fluid that's entering. And obviously you multiply that with the mass flow rate of the fluid that's entering, and you would get the you'd get the inlet flow work that is required so that the fluid enters the system. And obviously you subtract the flow energy that is leaving the system, and you do that by multiplying the mass flow rate that's leaving the system with the pressure at the boundary from where it is leaving the system, and multiply that obviously with the volumetric density. And then the energy generation term, you could leave it as is. Now, in most of your thermodynamic textbooks, what you're going to see is a rearrangement of this equation. So they move the flow work terms into these brackets. And it just makes it easier for you to deal with the inlet terms and the outlet terms. So if we rearrange this equation, now you have the change in the total energy of the system is equal to the mass flow rate of the fluid entering, and you multiply that obviously with all the components. So the internal energy of the fluid, the flow work that you need to apply on the fluid so that it can enter, and you multiply that with the fluid's kinetic energy, and you multiply that with the fluid's potential energy. And you subtract that from the energy that is leaving the system, and again, it is its internal energy of the fluid that is leaving the system, and kinetic energy and potential energy, and you also must add on to that the energy required to push against the pressure at the boundary, which is the PV at the outlet. Now, You also, to account for all of the energy balance, you must not forget these three terms at the end, which is the heat added or removed from the system, plus the shaft work, if there is any, plus if there's any generation of energy inside the system due to electrical, nuclear or a chemical reaction, for instance. Okay, so now looking at this energy balance term, there's another simplification that you could make, which is, let me introduce the term enthalpy to you, which is represented by capital H. Now, this enthalpy term is the internal energy plus the pressure times the volumetric density of the fluid. And therefore, if that is the definition of enthalpy, then you can combine the internal energy term plus the pressure times the volumetric density into just a capital H. And so if you do that, you get a much smaller energy balance to work with. And this enthalpy, you'd study it a lot more in thermodynamics, but there are so many definitions that you can come across and describe enthalpy, and one of which is it represents the heat content of a fluid, is one of the definitions that you might come across. And in order to find an enthalpy or the enthalpy of fluids, you'd find tabulated charts and correlations that you could use to find the enthalpy of a fluid. So for instance, if you look at the steam tables, you'll find the enthalpy of the fluid of water essentially, or you can find the enthalpy of steam at different temperatures and pressures. And essentially you would use that value in your energy balance to see what is the total change of the system's energy if you want. Now, this energy balance equation we looked at in terms of a change in energy over a finite time. But we are more interested, you'll find that we are more interested to find this energy balance or to express it on a rate basis. So instead of finding the change in the total energy, let's say in 1 or 2 hours on a specific time, we want to find it on a rate basis. So that just means that we take the derivative. Essentially, we keep the derivative of the energy of the system with respect to time. And that will give us the rate of the change of energy of the system. And so now what changes in how I'm expressing this is really not so much. In fact, only the mass flow term over here, I've put a dot on top to represent that I'm talking about a mass flow rate. And so this would be probably like kilograms per time. So kilograms per second or kilograms per hour. And then obviously these other three terms here, I want to distinguish them from when I was talking about a finite time, because I'm talking on a rate basis. Then Q dot here represents the heat that's being added or removed, let's say per hour or per second. So on a rate basis. And the shaft work here is also being represented in time rate basis. So it could be like joules per second, so something of that sort. And also the energy generation term is represented with a dot, so this is on a rate basis. So it could be like kilowatts, which is kilojoules per second, or it could be whatever rate basis that you define. Okay, so now that we know what the energy balance looks like on a rate basis, let's do some additional simplifications. First, in a lot of problems, you'll find that you can assume steady state, which means that there's no accumulation of energy inside a system. So that means the energy change of a system is zero. So that means any energy that's added to a system must leave the system. We can also see that in a lot of problems, you can assume that the shaft work is negligible. Or if you have tanks that don't have any mixers, you could just assume that the shaft work is zero. And if you don't have any chemical reactions or any electrical energy generation, then more often than not, your energy generation term here would be zero. And also you could assume that the kinetic energy and potential energy variations are negligible. So that means kinetic energy changes equals zero and potential energy changes equals zero. And that is the change from the kinetic energy from the outlet with respect to the inlet, and the same thing, the change in potential energy of the outlet with respect to the inlet can be zero, because let's say if you don't have any elevation, or if it's a horizontal pipe, then there's no change in elevation, then obviously the potential energy would be zero. And also you could make an assumption that the kinetic energy change is zero. So if the flow rates or the velocity of, let's say, the fluid flowing through the pipe section that you're interested in is the same, then if the velocity at the inlet and the outlet are the same, then you can cancel them and it would be approximately zero. Okay, so after doing all of these simplifications, what you have left is the energy coming in to the system in terms of enthalpy, and the energy leaving the system in terms of enthalpy is what results in heat that it can be either added to the system by the surrounding or removed by the system to the surroundings. So this means that if we truly have a steady state system, if the enthalpy of the liquid leaving the system is higher than the enthalpy of the liquid coming into the system, that means that this extra energy that the fluid has as it's leaving the system must come from somewhere. And this energy that you can calculate, that which is Q dot, that would be coming from the surrounding. Similarly, if the energy leaving the system, the enthalpy leaving the system, is less than the enthalpy coming into the system, then that just means one thing. That means that there is an amount of heat, which you can calculate using this equation, an amount of heat that must have left the system as before the fluid leaves the system. And that is what you would calculate here as the Q dot. And so what this equation is telling you is that the heat exchange that you have with the system and the surroundings really is dependent only on the change in enthalpy of the fluid as it comes in and as it leaves. And you know what? If the change in enthalpy is zero, then there is no heat exchange. This is basically what this equation is telling you. So do not get too caught up on the mathematics and the equation as much as I want you to be able to imagine what is this equation trying to represent, and whether or not you actually have a steady state system or not. Because if you don't have a steady state system, then this equation might not be valid anymore, because what's happening is the energy of the control within the control volume might be increasing. So you have to be aware of the assumptions that we're making here. Okay, so we can also simplify this equation further, but it only applies to certain cases. But I want to show it to you anyways. So we know that Q dot is equal to the mass flow rate multiplied by the change in enthalpy. And when I say change in enthalpy, it means the outlet enthalpy minus the inlet enthalpy. Also, there's an assumption here that I've made, which is the mass flow rate coming in and the mass flow rate leaving. They're both equal. So keep that in mind, because otherwise I wouldn't have been able to simplify this mass flow rate and take it out and subtract the enthalpies from each other. So looking now at this equation, we can make a further simplification, and I'll show you what cases it applies to. But essentially, you can calculate what the heat exchange is if you know the fluid's heat capacity and you know the inlet and outlet temperatures. Now, this is another way to be able to calculate the heat exchange without knowing the enthalpies. So as long as you can measure the fluid's temperature at the inlet and the fluid's temperature at the outlet, and you know its heat capacity and flow rate, then you can calculate the heat exchange of the system. So I'll explain what scenarios this applies to in the next slide. So without further ado, see you in the next video.